So in this experiment, you're going to determine the molarity and the mass percent of acetic acid in commercial vinegar. So this is split up over 2 weeks. The first week we're going to standardize a solution of sodium hydroxide. So what does it mean when you say you're going to standardize the solution? That means you're going to determine the concentration of the solution. So we're going to determine the concentration of the sodium hydroxide solution. And this is going to be done by titration. So titration is a procedure in which the concentration of an unknown reagent is determined using a known reagent through a monitored reaction. So in this case, our unknown reagent is the sodium hydroxide solution. We don't know the exact concentration of the sodium hydroxide. That's what we're trying to figure out. And the known reagent is KHP, which, by the way, does not stand for potassium hydrogen phosphorus. This is an abbreviation, not a chemical formula. It's an abbreviation for potassium hydrogen phthalate. The exact formula and molar mass for that is given in the lab write-up. So you're going to weigh out a set amount of solid potassium hydrogen phthalate, somewhere between 1.5 and 2 grams. The exact mass is not important as long as you record the exact mass that you use. So you want to record this mass to every decimal place the balance gives you, which should be to 3 places past the decimal. So you're going to dissolve the KHP in 100 mils of water in a 250 ml flask, and then you're going to add 2 drops of phenolphthalein indicator. Okay, so what's the purpose of this indicator? It's an acid-base indicator. It changes color depending upon whether the solution is acid or acidic or basic. Phenolphthalein is colorless in acid solution and pink in basic solution. Well, I'll talk more about that in a minute. So your NaOH will be added from a burette until the reaction is complete. And how are you going to know when the reaction is complete? When the solution turns pink. Alright? So you're going to open up the stopcock on the burette and let the sodium hydroxide solution start draining out. You want to shoot for a drop of about 1 drop per second. Some things you can't rush, and a titration is one of those. It's better off to take your time, because if you get going too fast, you'll shoot very quickly, shoot way past the end point. So as you get closer to the end point, you will get a warning. You will start to see local color changes around each drop. The drop of sodium hydroxide will turn pink as it goes into the solution, and then when you swirl it, it goes away. That's giving you a warning that you're getting close to the end point and that you should start to slow down. Once all the KHP is exhausted, the next drop of NaOH that goes in, the next drop of hydroxide turns the solution basic, and the entire solution turns pink, and that's how you know when to stop the titration. Right, so here's going to be your setup. The 250 ml flask with the 1.5 to 2 grams of KHP one more time. Record the exact mass, dissolved up in 100 mils of water with the 2 drops of phenolphthalein indicator. And here's your burette filled with the unknown sodium hydroxide, right? So you're going to open up the stopcock, let sodium hydroxide, drain in slowly, 1 drop per second. Once all the KHP has been used up, The next drop goes in. There's no more KHP for the NaOH to react with. The solution, now there will be an excess of hydroxide in solution, and the indicator will do its thing, and the solution will change from colorless to bright pink, and that's how you know when to stop the titration. So how do we do the calculations for this week 1 for this standardization of the sodium hydroxide? Well, you have to know that KHP reacts with sodium hydroxide on a 1-to-1 basis. Now, KHP is our known. That's our known reagent. So we know how much we're putting in, and we know what it is, so we know the molar mass of it. So your moles of KHP will be the mass of KHP divided by the molar mass. Okay? Then you take into account the fact that they react on a 1-to-1 basis. So the moles of sodium hydroxide equals the moles of KHP. So we're halfway there. We now know the moles of sodium hydroxide, but what we want is the molarity, which is the concentration, or moles per liter. So you divide that by the volume of NaOH that you titrated. And that is simply the final burette volume minus the initial burette volume. And of course you'll have to pay attention to your units, because molarity is moles per liter and your burette volume will be in milliliters. So you'll have to do a unit conversion on the volume. So what about week 2? So week 2 is where we actually titrate the vinegar. So you'll determine the molarity and the mass percent of acetic acid in the commercial vinegar. Now acetic acid is HC2H3O2 or CH3COOH. Seen the formula written both ways, but in both ways you have one hydrogen that's written separately from the others to indicate that that's the ionizable hydrogen. This is a monoprotic acid, mono meaning one, it only has one ionizable hydrogen. So we're doing the same basic procedure. You're still filling, you're still titrating, you're still filling the burette with the sodium hydroxide solution and titrating with sodium hydroxide, except that we're going to do the calculations in reverse. Now we're using the base to determine the concentration of the acid. Now the base is the solution of known concentration, and your vinegar solution is the solution of unknown concentration. So we're going to have two burettes. You're going to fill one burette with commercial vinegar, and you're going to fill the other with standardized sodium hydroxide solution. Now we're not actually titrating with this first burette, the one that has vinegar in it. You're simply going to use the burette to dispense and accurately dispense a set volume of the vinegar. Okay, burette can do that more accurately than, say, a graduated cylinder. So to measure out your vinegar, you're going to first clean and dry a 250 ml flask. And you're going to weigh the flask empty and record every digit that the balance gives you. Then you're going to dispense 10 to 20 ml of vinegar from the burette. That's the first burette that's filled up with the commercial vinegar solution. The exact volume is not critical, as long as you know the exact volume that you use, right? So you're going to record the initial volume of the burette, and then you're going to drain out somewhere between 10 and 20 mils, and then you're going to record the final volume of the burette. And that's how you get the volume dispensed. That's the final volume minus the initial. This is the volume of vinegar that you titrated. But we're also out to get the mass percent, so you're going to have to know the mass of vinegar. So after you add the 10 to 20 mils, you turn around and you weigh the flask plus the added vinegar, right? And you subtract this from the initial mass. Or rather you subtract the initial mass from this mass. And this is the mass of vinegar that you titrate. So we're going to know the volume of vinegar titrated, and we're going to know the mass of vinegar titrated. Okay? So we're going to titrate the sample in the same exact way that you did before. That is, you're going to add 2 drops of phenolphthalein indicator and titrate it with sodium hydroxide just like you did in the first week until the solution goes from colorless to pink. So how do we do our calculations for the molarity? So what are the units on molarity? Molarity is a concentration term. It's moles per liter. So the molarity of the vinegar will be the moles of acetic acid in the vinegar divided by the volume of the vinegar that you titrated. Right? So the moles of sodium hydroxide, that's our titrant, that's what the burette is filled with, will be the volume in liters times the molarity in moles per liter, right? The molarity of the sodium hydroxide, that's what we figured out in the first week. So a concentration term, moles per liter times liters, gives you moles, right? The liters are going to cancel. The liters will cancel. And that gives you units of moles. So that's the moles of NaOH. And then you take into account the fact that the vinegar and the sodium hydroxide react on a 1-to-1 basis. So moles of vinegar will be equal to, moles of acetic acid in the vinegar will be equal to the moles of sodium hydroxide. Okay, so then you can calculate the molarity of the vinegar. Now how do you do the calculations for the mass percent? This is why we had to know the mass of the vinegar that we titrated. So the mass percent is the mass of one component divided by the total mass. So in this case, it's the mass of the acetic acid in the vinegar divided by the mass of the solution, or the mass of vinegar titrated. You see, vinegar is not pure acetic acid. It's a solution of acetic acid dissolved up in water. So one more time, it will be the mass of the acetic acid in the vinegar divided by the mass of vinegar, the mass of the solution titrated. That's what you're titrating, is the vinegar times 100 to convert it into a percent. Okay? So how do we get the mass of acetic acid? We already know the moles of acetic acid. We determined that up here during the course of the titration. So the mass of acetic acid will be the moles times the molar mass. Molar mass you can calculate, right? That's just the number of grams to make 1 mole, so you're going to add up the mass of what? Of 2 carbons, 2 oxygens, and 4 hydrogens. Okay, you can calculate that out to 2 or 3 places past the decimal. So the mass of the solution titrated, that's basically your mass of your vinegar solution. So one more time then, your mass percent is the mass of the acetic acid in the vinegar divided by the total mass of the vinegar, mass of the solution that you titrated, times 100 to convert it into a percent. And that's how you do the calculations for the molarity and the mass percent. Now, there's some things that you need to know about working with the burette, and titrations are important, and we're going to do more of them, so you need to know how to do this properly. So your burette is used to accurately dispense volumes of liquids. It's a long, skinny tube with lots of graduations on it. Okay, so each graduation is 1/10 of a mil. So if you look at a burette, it'll look a close-up of it would look something like this. So each one of these represents 1/10 of a mil. So this is 17, let's say. This would be 17.1, 17.2, 3, 4, 5. The 5 line is longer, 6, 7, 8, 9, and then down to 18. But each line represents 1/10 of a milliliter. But as is common with reading glassware, you can estimate one more digit than you can read directly off the scale. So let's go back here and look at this again. Inside a burette or any glassware, water forms this curved surface called a meniscus. The thing about reading the meniscus is that you always read the bottom of a meniscus. You always read the bottom, not the middle, not the top, you read the bottom. Okay, so we're going to read the bottom of the meniscus. Now, we can, like I said, we can estimate one more digit than we can read off the scale. If this is 17.5, then this is 17.6. We know we're between 17.5 and 6, so we can estimate how far between here and here we are. We're clearly past the middle part. We're closer to 17.6 than 17.5, so you would read that to 2 places past the decimal. I would call it 17.58, but the point is that's 2 places past the decimal. So when you read a burette, you read to the tenths place and estimate to the hundredths place. So every burette reading should be to 2 places past the decimal. Another thing about working with a burette is that you always record the volume you see. You do not subtract volumes from 50. Okay, so if you go back and look at this again, the numbers go down as you go higher up. If you go all the way up to the top, the 0 is at the top. So the volume on the burette is actually 0 when it's filled all the way to the top, as strange as that might sound. So if it's filled right up to the top and it's exactly on the 0, then it's 0.00. It's not 0, it's not 0.0, it's 0.00 if it's right on the 0. And you do not subtract your volumes from 50. So when the burette is filled all the way up to the top, the volume is 0. You record the numbers that you see. And one last thing about working with the burette is the stopcock. That's the valve that you can open and close to dispense solution. The stopcock is open when it's parallel and closed when it's perpendicular. All right. So when you start your titration, it's perpendicular. The stopcock is perpendicular. You want to be sure it's perpendicular when you fill up the burette. Okay. When you start the titration, you turn the stopcock ever so slowly, okay, until you turn it towards being parallel. One more time. Closed is perpendicular. Open is parallel. Alright, so you'll want to open, when you start the titration, you'll want to open this up carefully, just a little bit, until you get that rate of about 1 drop per second. And that pretty well wraps this up.